So yesterday we were discussing the Faraday's experiment, in which we discussed how a changing magnetic flux has a tendency to produce electrical effects. Okay. So yesterday what we did, if you remember, I told you that we have a bar magnet. Okay. This bar magnet produces magnetic field, and it starts from the north pole and it terminates at the south pole, right? And in front of this bar magnet we kept a coil which was connected with a bulb, and we noticed that if the bar magnet and the coil were at rest, the bulb doesn't glow. But if I give some motion to the bar magnet, see, when I give some motion, what is happening? The bulb here is glowing. Why is that happening? The reason was the magnetic field which gets linked with this coil is changing, therefore the flux is changing. When the flux is changing, we are seeing that the coil doesn't accept the change. And because it doesn't accept the change, it produces its own magnetic field such that the original motion of the magnet is opposed. If you remember, if you understand the concept, when the north pole is approaching, you are seeing that, see, the positive direction of the current is like this, current is flowing like this. When current flows like this is anti-clockwise, counterclockwise direction, and counterclockwise direction, I told you yesterday, it generates north pole. So north and north will repel, due to which the motion will be slowed down. Similarly, when it is taken out, the south, see, when it is taken out, what is happening? The current is flowing like this. The south is going away. The coil doesn't want the south pole to go away. Therefore, it generates its own south pole. It generates its own north pole. How is that? See what is happening. When I am taking the bar magnet out, the current is flowing in anti-clockwise direction. So therefore, this side will be north and this side will be south. On entry, what is happening? North is approaching. This doesn't want north. Therefore, this will be north and that one will be south. But when it is going out, this is north and the other one is south. So the polarity is getting reversed and the bulb is glowing only in one case, whenever there is relative motion. And I gave you all the other cases in which I showed you how do we change the flux. Sometimes this will be set in motion, sometimes this will be set in motion, sometimes both will be in motion but with different velocities. If both are in motion with same velocities, nothing happens. So we came up with the various cases where we are seeing that the change of magnetic flux leads to the generation of the electromotive force, the EMF, due to which this coil generates its own current, and when the current is developed, that current opposes the original cause as per the Lenz's law. So we discussed the equation of the EMF, E is equal to delta phi divided by delta t, and the negative sign for the direction. Is that clear? Now today what we are going to discuss is an electromagnet. Now see, what is an electromagnet? A coil, okay, simple coil, which I want to connect it to the battery. Now what is happening? You need to understand. As per the concept, as you already understood yesterday, let me show you. If you remember, yesterday I told you, when the current is flowing in the clockwise direction, which pole gets generated? South, isn't it? And when the current is flowing in anti-clockwise direction, which pole gets generated? North, isn't it? Now understand what is happening. This is the battery, and this battery has been taken into consideration. It has been connected with a coil. Okay. So this is the positive end and this is the... Is that fine? Now what is happening? When I connect the battery across the terminals, the current will flow. Current flows from positive to the negative. So when the current is flowing, see, current will flow like this, isn't it? So which pole will get generated here? See what is happening here? Current is flowing like this, see, like this. So it is anti-clockwise direction, isn't it? When it is anti-clockwise, that means this pole will be north, isn't it? And this will be what? South. Is that fine? Therefore, you remember when the coil generates north and south, it will generate its own magnetic field. Therefore, the magnetic field will be something like this, from north to south, from north to south. And inside, it will be from south to north, isn't it? Yes or no? So, we are having a magnet, but this magnet has been generated with the help of current. Therefore, we call this as an electromagnet. The Dubai police uses most of it, this phenomena, to lift the cars when they are parked at the wrong places. They are using electromagnets. That electromagnet is, they keep it over the bonnet of your cars and the car gets attached to it. They take the car along with themselves and find the person, whosoever has violated the rules. Electromagnets. Their strength, see, the natural magnet, which was like this, the North Pole and the South Pole, it is natural. Its strength is fixed. But for this magnet and its polarity, its strength and its polarity, both are fixed. Isn't it? The strength is fixed. You cannot increase or decrease the strength of the natural magnet. You cannot change its polarity. If this is north, this will never be south. Always, this will always behave as a north pole. This will always behave as a south pole. But here what you can do is you can change the strength, you can change the polarity, you can do anything with this magnet. The electromagnets find their applications several places, like the escalators, The escalator, when you go to Lulu Exchange or Lulu Markets, when you take your trolley along, on the escalator, you might have noticed that the trolley, although all of a sudden sticks to the floor, isn't it? What is happening? The reason? Electromagnets. Current is flowing, and due to which it produces magnetic field. The wheels are magnetic, they get attached. Khalas. So electromagnets are finding their applications everywhere. Now what is happening? First of all, take a picture because everything will get erased. Now I'll show the simulation after this. Everyone, did you click the picture? Now see what is happening. Initially, no magnetic field is there, okay? Because the battery is not 0 volts. Now what I do, I increase the voltage to 5 volts. See what is happening. When the battery of 5 volts is connected, this is the positive terminal, this is the negative terminal, okay? The current is flowing like this, so the magnetic field will be generated like this. So the magnetic field, like I showed you, will be from it will be from north to south from the outside. North to south from the outside. Is that fine? And inside it will be from south to north. Therefore, see the compass? The compass is pointing like this. That means this is the direction of the magnetic field lines. Okay? That means this is the north and this is the south. Okay? Is that fine? And now see. First of all, the number of field lines that are visible to you, that are prominent on the board. If I increase the strength of the current or the voltage source, more current will flow. When more current flows, more magnetic field. See? Do you see more prominence now? The prominence of the magnetic field lines increases when the voltage is increased because more current flows here. Is that fine? One more thing that we could have done. The number of loops here, the number of loops, 1, 2, 3, 4. 4 loops, we are seeing the number of prominent lines, okay? Now, if I decrease the number of loops, see what will happen? Do you see they are fading away? So, again, the strength of this magnet can be changed depending upon the number of loops. Not only the change in the battery. If we change the battery, if we increase or decrease the voltage, the external voltage, we can increase or decrease the strength of this magnetic field. If we change the number of loops, we can change the strength of the magnetic field. Is that fine? Second important thing. If we reverse the polarity, see, if I reverse the polarity, now this was the positive end and this was the negative end, okay? Now if I reverse it, that means this will be negative and this will be positive. So what I'll do, this will be 0, okay? And then I'll reverse it, I'll take it in the opposite direction. Now the current is flowing in the reverse order. This is the positive end and this is the negative end, okay? So what is happening, see? This is the positive end and this will be the negative end, okay? Now the current is flowing something like this, okay? So when the reverse happens, now this is the north pole and this is the south pole. So the magnetic field has reversed, see? Magnetic field has reversed. When the magnetic field has reversed, we have changed the polarity of this magnet. That means it is not like the normal magnet which has a constant fixed polarity. The polarity can be changed. This was north, this is south, always. But here, the same thing has changed depending on the connections that you have given it with the battery. The way you have connected it with the battery. So if you are able to change the polarity, you can change the direction of the magnetic field. Point number 1. Point number 2, if you increase or decrease, what will happen? See? If you increase or decrease, again the same things will happen. See? The magnetic field lines are getting prominent and fading away depending on what? Depending on the strength of the battery. If you are increasing the strength, more prominent lines. If you are decreasing the strength, less prominent lines. At 0, no magnetic field. So, and if you want to use it as a magnet, you just have to apply the battery. You don't want to use it as a battery, switch off the battery, khalas. You switch it off, it will not behave as a magnetic. And if you increase or decrease the voltage source that you are connecting to it, it can increase or decrease the strength of the magnetic field. Along with that, again, if you want to do the same thing, you can increase or decrease the number of loops. Less loops, less magnetic field. More number of loops, you are seeing more magnetic field. So can I say that the magnetic field which is getting generated in this system depends on 2 things. 1, the current. More current, more magnetic field, isn't it? Second, very important thing, the number of loops. More number of loops, more magnetic field. Less number of loops, less magnetic field, isn't it? Therefore, remember the equation for electromagnets. The equation is this. The magnetic field is directly proportional to the number of loops per unit length. What does this mean, number of loops per unit length? For example, the length of the magnet is L, okay? And there are 4 loops. So small n is total number of loops divided by the length. Is that fine? More number of loops, more n, more will be small n. When there is more number of greater value of small n, there will be more magnetic field. One more thing, the magnetic field is directly proportional to the current. More current flowing, see, when you are increasing or decreasing the battery, the voltage source, what is happening? The prominence of the magnetic field lines fades away or increases depending on the strength. If you are increasing the strength, more magnetic field. Decreasing the strength, less magnetic field. So remember the general equation for the magnetic field inside in an electromagnet, it is equal to magnetic. Yeah.
What was that?
And the number of turns per unit length. See this. Number of turns per unit length. Is that fine?
Yes. And what was I?
I is the current. The current flowing through this tube. Okay? So the equation from first and second, what do we conclude? The equation is this. Okay? And if you want to remove the proportionality sign here, we can write it as magnetic field is equal to mu naught times Ni, where mu naught is called as the permeability. What is it called? Of free space. It has a value of 4 pi into 10 to the power negative 7. Okay? So if the question is asked, you should be able to solve it.
Is it B equals to M times Ni?
Mu naught. This constant is mu naught, which is known as permeability of free space. It is the
Is it Ni or N times I?
N times I. It is mu naught times N times I. And what is N? N is total number of turns per unit length. Click a picture of this for the magnetic field.
What's N?
N number of turns per unit length. M? Where is M?
N.
Mu. You pronounce this as mu.
M-E-W.
Yeah.
What was the
And you write it like this, see?
What was the definition?
The permeability of free space. The ease of the magnetic field lines when they travel through the vacuum. Okay, how easily can magnetic field lines propagate through vacuum? The value is 4 pi 10 to the power negative 7. Okay? Yes? I is the current. See, this is the positive terminal, so the current is flowing like this. This is positive, this is negative, so the current will flow from the positive terminal, come like this, like this, like this, so finally go like this. Come like this. So when the current flows in this way, we have the south pole, right? And like this, from here it will be north. So therefore the magnetic field will be like this. It has been made clear yesterday as well, the direction of the magnetic field. Remember, you need to know what is the direction of the current, and then follow my rule of the dayara, the circle that I showed you. South or the north, depending on whether it is clockwise or counterclockwise. Is that fine? Is it clear? Yes? So this is one of the applications of the Faraday's concept. Now one more concept, one more beautiful concept. Have you seen your iPhone chargers?
Yes.
Do you know these iPhone chargers take up some current from the outside? The voltage is very high, isn't it? The outside voltage, if you see, it is 220 volts. It can be more, it can be less. But if you go for the ratings of your adapter, it is written 5 volt output. Isn't it?
Yes.
How is it managing that?
Rejects those.
No, it doesn't reject the rest. It helps, it takes the help of the Faraday's concept. And the concept is of a transformer. Should I erase this? See what is happening.
Or it can only have like a specific amount of voltage.
What?
It can only have a specific amount.
Yeah. Here is the concept. The concept is of a transformer. Now, what is a transformer? First of all, you need to understand what is a transformer. Now, when you talk about a transformer, you need to understand that it is a device which helps to transfer energy, okay, from one place to the other place, okay. It helps to transport power. The power which it has a tendency to transport this power without losing this power, okay, at a constant, at a fixed rate. Fine. So when you talk about a transformer, this transformer is present in our adapters as well that you have for your mobile phones. So what is happening? You need to understand the concept. The concept is that it consists of an electromagnet, okay, and then it consists of a pickup coil, okay, and to this pickup coil your phone is connected, okay. Here you have your mobile phones. This is your iPhone. Instead of the bulb, it is your iPhone. Just think like that. So what is happening? See, instead of this battery here, you put it in the socket, isn't it? So there's a coil, there are two coils in this system. One is called as the primary coil, and this is called as the secondary coil. Okay, there are two coils, the primary and the secondary. Understood? So what is happening with the help of primary and secondary? The primary coil has a voltage source already connected to it. It is connected with the socket. Okay? But the secondary coil is not connected with anything. It doesn't have a voltage source. Therefore, this bulb here cannot glow. Therefore, this phone here cannot show the charging is on. Okay? Then what happens? How does it show that charging is on? See what happens. When you plug the adapter into the socket, what happens is the current starts to flow in this coil. Okay? In this coil only, called as the, which coil is this called? This is called as the primary, and this is called as the secondary coil. Okay? In the primary coil, understand very important thing. When the current starts to flow, will it produce its own magnetic field? Yes? Isn't it? When the magnetic field is generated by this coil, that magnetic field gets linked with this. When the magnetic field is generated, the magnetic field, for example, it is like this, north to south, north to south. Now these field lines, this and this, these field lines get linked with the secondary coil. And the secondary coil initially was at rest. There was no magnetic field. Okay? When there was no magnetic field, what happens is, this coil doesn't want the magnetic field to come through it. Therefore, as per the Faraday's induction, it produces its own current, such that these field lines do not enter. When it produces its own magnetic field, therefore it runs its own current, and that current helps this bulb or this mobile phone to charge. The phenomena is called as mutual induction. Mutual. Why? Because there are two coils. The two coils are working in unison. This coil is connected to the battery, the current will flow, it will produce its own magnetic field, the magnetic field in the previous case that we understood, okay? Now that magnetic field gets linked with the secondary coil. This coil was at rest, it has inertia, it was at rest, there was no magnetic field link. Like in the previous case, when the magnetic field linked to a coil changes, it produces its own magnetic field. Therefore, it produces its own magnetic field such that it opposes the original magnetic field. For that, it has to produce current, and that current is the electromotive force, and that current helps this bulb to glow. Now see the simulation. Click a picture of this first. Click a picture, I'll show what is happening. See what is happening. See, this adapter is not connected with anything initially, okay? So there is no magnetic field. Is the, for example here, what is happening is this, instead of the bulb, understand that it might be your mobile phone connected, okay? See what is happening. The moment you plug in the charger, to the socket, for example, here is the case. See what is happening. This coil has current flowing through it. Therefore, it has produced its magnetic field. Has it or has it not? Yes? Now, the motion takes place. When the motion takes place, see there, what is happening? This bulb is not connected with any voltage. Your phone is not connected with anything. But see what is happening when the coil is coming closer or going away. The magnetic field, these magnetic field lines, the red ones, the white ones, they are getting linked to this coil. This coil doesn't want it. And for that, it produces its own magnetic field, so that it will oppose the original. And to produce that, it has to allow the flow of electrons, the current flows through it, and that current causes this bulb to glow, similar to the way that we studied yesterday. Is that fine? See what is happening. When it goes closer, 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 see? Goes back, again, there is flow, there is flow, there is flow. So, understand, very important thing. The second realization that you will have. The current here, is it flowing very fast?
No.
Yes? As compared to here, see. The flow here is fast as compared to the flow which is here, isn't it? But now see what is happening. Now see what will happen. Now see, when the current in this loop is flowing, I increase the strength of the current which is flowing through this. The current flowing here is very less, isn't it? Do you see that? Your input voltage that is coming from the outside is 220 volts. But when you have to plug in your iPhone or your mobile chargers or whatever, you see that the adapter rates 5 volts. 10 volts, isn't it? So that means the voltage has to reduce. It cannot always keep it at 150 or 200. Why? Because your phone might burst. It will burn if more current or more voltage is applied across it. You will undergo a short circuit. So therefore, this mechanism works in such a way that even if the current here is very high, the current here which flows in the secondary coil is less. Very less current flows, and that is how your phone always remains safe. Okay? So what is happening? See, you need to understand the mechanism here. The current is flowing like this, so that means which pole is generated here? The north pole, isn't it? Here it is north and here it is south. So let me show what is happening. This is north and this is south, isn't it? Because the current is flowing like this. Like this. Okay? Magnetic field lines. When the north pole is approaching this coil, what will happen? Will this coil like the approach of the north pole? No. When it doesn't like the approach, so it will produce its own north pole, isn't it? For that, to produce the north pole, what should be the direction of the current? Yes? Counterclockwise. So that means in this loop, current will flow like this. Okay? So current will flow like this. Now see the motion of the electrons. When I take it towards it, the motion of the current will be something like this. That means like this, it will go up. These positive charges will go up. See, is that happening or not? See? Yeah, see? These positive charges will go up. See? See? Do you observe they are going up? Do you observe they are going up when I am bringing this coil very close? Do you observe that they are going up? See? Yes? Because they don't like the approach of the North Pole. They don't like the North Pole approaching, therefore they produce their own north here, south here. And that north will repel the coil coming towards it. Due to which we are seeing this bulb will glow. Whatever is connected with the secondary coil glows. So this coil senses, but this coil produces. This is the primary coil. It produces its magnetic field. The secondary one, it senses the magnetic field. In order to oppose that, it produces its own magnetic field. Now this is the principle of a transformer. It's a device which conducts energy at a constant power. Okay, and this device works in such a way that it has two coils. One is already connected with a source, the other one is not connected with a source. The first one produces its magnetic field, the second one senses the magnetic field, the change in the magnetic field, and when that change takes place, it produces its own magnetic field, and due to that, the bulb or the external environment gets lit up. Is that fine? Now see what I'll do. I'll change the battery here. I'll convert it to a AC source. AC is the alternating current. The positive and negative are not fixed. They are constant. Okay. They're not constant. They are continuously changing. Okay. The positive and the negative, we don't know whether this is positive or this is positive. This keeps on changing. This is the current that flows in our homes. Okay. Now see what is happening. I don't need to, see what is happening. Is there any motion?
Yes.
Where is the motion? There is no motion. Am I bringing it away or taking it closer? No. But it is still glowing, isn't it? This is exactly what happens inside the adapter. Now inside the adapter, this doesn't move. This is kept at a single place. This is kept at a single. Your adapter doesn't get bigger and smaller, right? It's fixed. The size is fixed. How does that change take place? How is it sensing and producing its own current? The reason is, here we do not have a DC current, we have an AC current. Which current? Now what is an AC current? See, understand what is an AC current. AC current is an alternating current. It changes its polarity itself. When the polarity will change, see what is happening? I'll show you. When the polarity will change, for example, initially, when I started, this was positive and this was negative. Tell me which magnetic field was produced. So this will be the north pole and this will be the south pole, isn't it? So the magnetic field was like this, isn't it? But within a very fraction of a second, what happens? The polarity gets reversed. When the polarity gets reversed, for example, this becomes positive, and this becomes negative. Now, this will be the north pole and this will become so the magnetic field, the direction of the magnetic field will reverse. When the magnetic field will reverse, so it will be something like this now. Isn't it? Now, this coil is again sensing the change in the magnetic field. Understood? Therefore, I do not need to change the position of this coil. This coil will be kept at a single place, but when it is at a single place and connected to an alternating source, what happens is I do not need to produce any physical motion. The change in the polarity produces different magnetic fields within fractions of seconds. Sometimes magnetic field is like this, sometimes it's like this, sometimes like this, sometimes. So due to which this coil, the secondary coil, is sensing that change. So when change takes place, it doesn't like the change. Therefore, it will produce its own current again, and that current will light the bulb always. Is that fine? That is how it works in a transformer, which is at homes, at the electrical substations, power grids, grid stations. Have you seen a grid station anywhere? Big transformers are installed. Electrical poles, have you not seen them? The electrical wiring that is connected between two big poles, towers. They are connected at the back end with a transformer, and that transformer is doing the same thing. This transformer is connected in your mics as well. The mic system. It works on the same principle. Delivering energy at a constant power, but the increase or the decrease in the voltage. Clear? See, now look at the mechanism. See? And if you observe this, what is happening? Sometimes the current is going up, sometimes the current is going down. Why? Because the polarity here is changing. It's north. When it is north, this wants to produce north here, isn't it? When this is south, this wants to produce south here. Therefore, it will also change its direction. This is the concept of a transformer. I don't need to, take it away or bring it closer. If I keep it at a single place, increase the supply and the frequency of the voltage source which is in the input, see, you are seeing that your bulb or your whatever is connected is getting lit up, it is getting charged, and this coil, the secondary coil, has a tendency to produce the energy, to produce the electromotive force by the phenomena of mutual induction. This is what happens. This is the concept of a transformer. Do you have any doubt in this? So the first thing about transformer is that it works on the principle of mutual induction. Okay, it has two coils, primary and the secondary. Primary produces magnetic field, secondary senses it. Okay, so when the secondary coil senses it, it doesn't like the change. Therefore, it produces its own magnetic field, and due to that, the current which flows lights up our bulb. Is that fine? Is that fine? Any doubt? This is the concept. Now, after this, we have the last concept, and that is the concept of a generator. Have you seen how is actually electricity produced? The power stations, the power grids, have you seen that? See what is happening. Again, the principle of Faraday. One of the beautiful concepts. See what is happening. In hydropower projects where we have water which is flowing, we generate electricity with the help of water. Like in my place, I come from Kashmir, we have enormous supply of water, okay? Because we are at a hill station, rivers are there, so due to that water, with the help of that water, we produce our own electricity. And it is very cheap, because we can produce it from literally scratch. See what is happening. Say for example, there is a stream, okay? There is a stream, and water flows through that stream, okay? What do? We take a turbine. Here is a turbine. This turbine is connected with a bar magnet. It's a big magnet which is connected to it. It has a north pole and a south pole, okay? And at the same time, we take a coil, a pickup coil, which is connected with something. Say for example, here I have shown the bulb. See what is happening. Initially, tell me, this bar magnet will produce its own magnetic field, isn't it? So that magnetic field will have a direction from north to south, something like this, isn't it? Yes? Now what happens? I keep this turbine inside the stream of water. The water is falling from a larger height. It's falling from a larger height. So when the water falls, see, I open the water here. See what is happening. When the water falls, it rotates the turbine, isn't it? Now the magnetic field, which is here, see the field lines, what is happening to the field lines? They are changing their direction. When the magnetic field is changing its direction, the coil doesn't like the change. When the coil doesn't like the change, it has an inertia, isn't it? And that inertia compels it to produce a reverse magnetic field. For that, electrons, the current has to flow, and here the bulb flows. This is how electricity is produced in my place. This is the hydropower project. This is on a small scale. Same thing happens on a very large scale. So what we have? We have a stream of water coming from a larger height, a big turbine, okay? And magnetic field, the bar magnet is connected to that, okay? So what happens? When the water falls on this, so that rotates, okay? When it rotates, the magnetic field which gets linked with the secondary coil, it is changing continuously in direction. Okay, when the magnetic field is changing continuously, this coil doesn't like the change. When it doesn't like the change, what happens? It induces EMF, and that EMF causes the current to flow. And when the current flows, khalas, this bulb glows. This is the concept. This is the concept of electromagnetic. This is the concept of Faraday. That is why I said Faraday did an amazing work. From nothing. See, and what is happening? One of the beautiful things. This is renewable resource. Why? The water that has fallen down, take it up with the help of a motor. Keep it here. Again, ask the water to come down. When the water is falling again the same. Same water. We don't need more water. Same water will again produce more energy, isn't it? Is it clear? But sometimes, there is the season of drought. When there is drought, water isn't there, and there is no water, we cannot produce electricity. Why? The reason is, the problem in our place is, we are not able to save this energy. We can produce it and we have to use it. We cannot save it. That's the problem. Is it clear? And see, if the speed of the turbine is increased or decreased, see, very important. If the water is falling down very slowly, the change is, 27.2 revolutions per minute. At less RPM, it is rotating, okay? When less, the current here is very less. When it is even lesser, see, very, very slow. The current here, the bulb is glowing but at a very low voltage. It's not bright. But if the water is flowing at high speed, the frequency, 57.8, it has increased. When the frequency has increased, see, the more the current is flowing in this loop, and due to that, the bulb is glowing very bright. Do you understand the concept now? Do you understand how is this being done? Here in Abu Dhabi or Dubai or Sharjah, do we have water like this? Can we produce electricity like this? Can we? We cannot. Then how do we do this? What we do, I'll tell you what we do. We take help of the windmills. Have you seen the windmills? Yeah? No, in deserts mostly. What they do is, they use windmill. Windmill, have you seen a windmill?
Yes.
It is a big fan, isn't it? Something like this. Yes? When the wind flows, okay, when the wind is blowing, these fans rotate. Same thing happens again. This is connected at the bottom with the help of a magnet and a turbine. That magnet rotates, and near to that magnet another similar coil is connected. When similar coil is connected, the coil will again sense the change in the magnetic field. When it senses the change in the magnetic field, what happens? It produces the electromotive force, and that electromotive force causes the bulb to glow. Lights up the whole village. In India, in Rajasthan, they use this technique. The concept of the windmills. Here, how do you produce electricity? Yeah, of course, it comes from the same phenomenon. Then they, transfer it from one place to another with the help of these wires, electrical wires. But the source is the wind energy. So this is conversion which is taking place. How many of you have bicycles with a dynamo? Bicycles that have those wires installed and a motor, something like that. No?
No, we have
Yeah, the electric. Yeah. Again, the same thing is happening there. Same thing. How does that dynamo or your beep work? When you ride the bicycle, okay, you're doing this. This is connected with a small magnet which is placed inside that box. and that magnet changes, magnetic field that rotates, and when it rotates it produces magnetic field, changing magnetic field. That changing magnetic field linked to a coil, the coil is compelled to generate its current. That's the mechanism of a generator. This is a generator. This is a generator. But here the generator is working on the principle of flowing water. Okay? That's it. And you are seeing when I'm causing this turbine to move, what is happening is that see, very important thing. The current which is being produced is again changing the direction continuously. Isn't it? So we are not getting a constant supply, we are getting an alternating supply, the alternating current. And that is the current that comes to our homes. The polarity is continuously changing, see? And remember, in one cycle, your bulb switches off 2 times. If you notice, see, dim and bright. It gets 2 times dim in one cycle, depending on the frequency. We can calculate in 1 second how many times does it, shut, does it turn off. In India, the frequency is 50. That means in 1 second, 50 cycles are completed. But in one cycle, it switches off how many times? 2 times. Therefore, our bulb in India switches off 100 times in 1 second. But we are not able to notice it. Can you tell me why? Yeah, fast is the persistence of vision. Our human eye is designed to notice something in 1/22 of a second, but that change is taking place for 1/100th of a second. And the previous image, do you know how video cameras work? They click pictures and those pictures are, they run at a very fast speed. Okay? And due to which the previous image which is on our brain is still there and the new images comes to the front. And our brain thinks that they are together, and therefore a video works. It feels like everything is in motion. Otherwise, there is nothing like video. People are clicking pictures, and those pictures are being run at a very fast speed. And similar thing happens with the bulb. The bulb shuts and turns on 100 times in 1 second. But because the previous image is still there, it feels like it was always on. Otherwise, it does shut. If you place a camera and decrease the speed and run those images at a very less speed, you will see how many times does your bulb shut off, turn on. Is that fine? So here, one more thing. Number of loops are increased, more current. So if we change the number of loops, we can increase or decrease the current. We are seeing what we need. It depends on what we need. That is what your adapters say. If your adapter is designed for 2 volts, the number of loops will be less or more? Less. If your adapter is designed for 10 volts, so more volt. So for that, more voltage, more number of loops. Is that fine? Similarly, we can increase the strength of the magnetic bar magnet which is here. We can, for example, if we increase the strength, see, more brightness of the bulb, more voltage, more current is being flown, more energy is there. Is that fine? That is the concept. We can increase or decrease the area. See, more area of the loops, the bulb is at its maximum. That's the concept. Is there any doubt in this? Anything that you would like to ask, because this is over and tomorrow I'm thinking of a curved structure called as the bronchostone, and I'll ask you a question. That question will be something like this. I want you to know. If there is a ball and that ball is coming from this point up to this point, okay? Point A to point B. It has 3 parts, 1, 2, 3, and maybe a 4th. Out of the 4 parts, along which path will this ball reach point B the first?
The
Last one?
Second one.
They'll reach at the same time.
Second or third.
Last one, why? So this is your question for tomorrow, okay? This is your question for tomorrow, but I hope everything is clear from the electromagnetic induction. We completed a unit with the help of simulations. Okay?
Yes.
Thank you so much.